Good morning and welcome back. I hope you're enjoying this series on C programming. The idea was to learn enough C to help you build your next projects, maybe build a new product or do your startup. The world opens up with one programming language in hand. So let's start with C. That was the whole idea. Today we are going to look at how a C program actually thinks. Because writing code isn't just about listing instructions. It's also about controlling which instructions run, when they run, and why they run. This episode is all about learning the tools that give your code a brain, decision making, repetition, structure, and it even gives us a glimpse into memory level control. So let's get started. The first topic is conditional logic, teaching code to make decisions. Every meaningful program makes decisions, just like we do. And in C, it all begins with the if statement. An if statement is your program asking a simple question. If this condition is true, should I run this block of code? If it's not true, the program just moves on. But life isn't always one directional, right? Sometimes if the if condition isn't met, you need an alternative. That's where if else comes in. So if this is true, let's do this, do A. Otherwise, do B. Now your program has a fallback. If the first condition is not met, it can do B. So when decisions get a little more complex, we have something called as the else if ladder. This takes over. The program checks one condition after another. So 90 and above? No. 80 and above? No. Until it finds the first true match. And if none match, the final else safely catches everything else. So when these ladders get really long, messy or repetitive, C gives us a much cleaner structure as well. And that's called the switch statement. Think of it as a menu system based entirely on one variable. The program jumps straight into the matching case. No climbing ladders, no checking everything one by one, just a clean, efficient branch to the right option. So by this point, your program has learned to make choices. Now it's time to give it the power to repeat actions. Loops. Repeating tasks automatically is loops. Computers are built for repetition, and C gives us three core loop types for different situations. We have the for loop, which is perfect when you know exactly how many times you want something repeated. It has three parts. There is a initializing counter. It's basically something you initialize with a value. Then you check a condition and then you update the counter. So start, check, update, repeat. It's structured, predictable, and ideal for counting tasks or looping through arrays. We'll talk about arrays later. Then we have the while loop. If you don't know the number of repetitions, the while loop steps in. It runs as long as its condition remains true. But there's one key detail. It checks the condition before running. So if the condition is false at the start, the loop doesn't run at all. That's the while loop. Then we have the do while loop, which is like you flip that logic and you get the do while loop. So it runs the block of code once at least, then checks the condition. So this guarantees that the loop executes at least once, no matter what happens. So this is great for menus, user prompts, and situations where showing something once is essential, at least once. So with decisions and repetitions in place, your program now has structure. Let's enhance that with more structure, which is called functions. Basically, you're turning logic into reusable building blocks. As programs grow, repeating logic everywhere becomes unmanageable. So this is where a function comes in. A function lets you create a neat, reusable block of code, and you can give it a name. So let's look at a function prototype. Before using a function, C requires that you declare it. This declaration, also called as a prototype, is like telling the compiler, hey, this function exists. You will see it later. Right now you haven't seen it, but it will be coming soon. Then we have the function definition. This is the actual code, the logic of what the function does. So it is basically the chapter that fulfills the promise made by the prototype. So if you look at the function prototype or the declaration, it is something like the index page of a book where you are listing out all the functions, all the chapters that will be in the book. So you know that this chapter is coming. You still don't know what's in the chapter. So if you go down to the function definition, this is the actual code. So the function definition is like the actual chapter itself. You have the entire content of the chapter. So this is the chapter that fulfills the promise made by the prototype. Now let's look at how do we call a function. You defined a prototype, you declared a function which is a prototype, then you defined the contents of the function, which was the chapter that you write in a book. Now how do you make this function call? How do you call it? This is pretty simple. When you actually use the function, wherever you call it, your program jumps to the logic, runs it, and comes back. And when I say call it, all you have to do is use the name of the function and the parenthesis following that. C will basically know that you are trying to invoke this function. It will go to that part of your code, run that function, and come back. If you remember about stacks, in the last episode we talked about how when a function is invoked, a clean sheet of paper is given to the function. That was the stack trace, or sorry, the stack frame, right? So when you invoke this function, the function is given a clean stack frame. It's a white sheet of paper. It can do all its work on that. Once the function finishes its work, that paper is thrown off. But the function was doing something on your behalf, right? It was doing a reusable piece of code for you. It has to return that to you. We'll talk about return values in a function. So yeah, even before we talk about return values, let's talk about passing data. Functions often need inputs. C gives you two ways to provide that. You can pass by value. The function gets a copy of your data. The original remains safe and unchanged. So for example, if you're adding two numbers and let's say you have int a and b, you can pass a comma b to the function. The function gets a copy of your data. Whatever is stored in your a, that value goes to the function. A itself is not given to the function. So the original remains safe and unchanged. The function will take the two values you passed, a and b, it will put it on its white paper, its stack frame, and start working on it. Once it has done the addition, it will return the value back to you. That is a return value. And then that stack frame is thrown, or the white paper is disposed. Your original a and b values remain as is. You only got the calculated addition back from the method. Your original a and b remain exactly the same. But there will be many cases where you actually want to modify the original a and b. You want to do a very complex calculation of a and b, and you want it stored back into a and b. In this case, you can pass the variables by reference. So the reference is basically the memory address. The function receives the memory address of a and b. You can do that by prefixing ampersand to a and ampersand to b. So instead of passing a comma b, what you will be passing is ampersand a comma ampersand b, which will basically pass the memory address of a. It is not passing the value in a. So that the function, once it opens up its stack frame, its white paper, it starts writing things on the white page, and it can also access the memory address that was passed. It can directly modify the original values of a and b because it has the memory address. It doesn't have the value. So if it wants to read the value, it can use an indirection. It can use star of the memory address, and then it can read the value out of that. If it wants to write back into it, it can use the same method. So with functions, your program becomes cleaner, more organized, and easier to maintain. And pointers give you a way of managing memory. So let's look into a little more details on how pointers and recursion works. Now that you understand structure and flow, it's time for two advanced concepts. So this will basically unlock the real depth of C. Let's look at pointers. It is basically direct access to memory. We just spoke about it. A normal variable holds a value. So when you invoke a function and pass it a normal variable, what the function gets is a value. It doesn't get the actual address of the variable. A pointer holds the address of a variable, a location in memory. It doesn't store the value itself, it stores where the value lives. So when you pass ampersand a to a function, what it gets is the address of a. It doesn't get the value of a. Why do you need the address? You can do a lot more complicated work when you have the memory location. You can modify or put the value back in the original variable without creating any temporary variables and those kind of things. So pointers matter because they allow functions to modify variables outside their scope. When you pass the address of a variable to a function, the function doesn't have access to the whole program itself. It is given a scope. It is supposed to work on that white sheet we gave it, right? We gave it a stack frame. It is supposed to work on that. But since you passed a address of a variable, the function now has access to memory variables which are outside of its scope. Why do we need all these things? We'll look at that in later episodes. It's just enough for us to know that if the function needs to work on something that it doesn't have access to in its scope, you have to pass the address of a variable. It is basically efficient memory management. You don't want to keep on replicating a value. Suppose you have a variable that holds one page of text, right? Thousands of words. If you want to pass by value, you are going to pass all the 1,000 words in that page to the function. But remember, the original chapter remains unchanged because you are passing by value. So the original chapter remains as is, and you are making a copy of those 1,000 words, passing it to the function, which will eventually do something and come back with some response. So it is redundant. It is basically wasting memory when you know that you want to modify this chapter. At that in such a situation, you can basically pass the address of the variable which holds the entire chapter text. So nothing is duplicated. It's just the memory address that is passed. The function can work on the chapter text directly. That is how pointers and addresses work. So it's basically efficient memory management. And it also helps in implementation of complex data structures like lists, trees, and graphs. We'll get into that when we talk about data structures. And it's faster and more flexible code. So they're one of the most powerful and defining features of C. Pointers and addresses are the references. Sorry, I meant pointers and references. They're one of the most powerful and defining features of C. Now let's look at a last topic for this episode, recursion. So recursion is when a function can call itself. So it's a technique where a function solves a problem by calling itself with a smaller version of that problem. We can go into details of recursion on how you can take a list of numbers and how we can sort it out. I'll take it up in a later episode because I want to keep this one short. I just want to introduce the concept of recursion when a function calls itself. So the two defining features of a recursive function is, first, there is a recursive step. Basically, you take a big problem, break it into a smaller chunk and pass it back to the same function again. So that guy takes the problem, breaks it into a smaller chunk, passes it back to the same function again. So that's how the stack builds up. Remember, every function call builds up a stack trace. It has its set of variables, values, everything written down. You invoke the function again. So what happens is it gives it another new clean sheet with a smaller problem. Again, you do the breaking up of the problem into a smaller chunk and pass it back to the same function again. You have a cleaner white sheet now with just the smaller problem. Again, you work on it. So you keep on doing this until you touch a base case. This is the simplest version of a problem where it cannot be broken down any further. So in this function, it has its white sheet, it has the simplest possible problem in its hand, it solves it and returns the value back to the caller, which was the same function. It called it with a smaller problem, right? So it gives it back that value. So that function now has the smaller problem's answer. It calculates the rest of it, passes it back to the caller, which is the same function on the stack. So it keeps on going that. And finally, it would have solved the whole problem by chunking the problem into smaller and smaller parts and passing it to itself. A typical example of recursion is basically factorial calculation. So if you have factorial of 3, I would basically chunk it down and call the same factorial function again with factorial of 2. And this time the factorial 2 would basically take the number passed, which is 2, and take the next smaller number 1 and pass it again to the same factorial. So all of it will eventually get evaluated and added back. So once it hits the base case, everything kind of unwinds and returns the final answer. Recursion offers elegance, simplicity, and powerful problem solving abilities. We'll look at all those things in detail in later episodes, but you basically understood what is recursion, where a function calls itself. You looked at what pointers are, how do we directly access memory. We talked about functions, prototypes, and its definitions. And we also talked a little bit about loops and conditional statements. So that is the basic structure you need to write a C program. Decisions, loops, functions. These are the foundational building blocks that control the flow of nearly every program ever written. They turn your plain text into software that thinks, reacts, it organizes itself, manipulates memory. With all these tools in your hand, you are not just writing instructions anymore, you are shaping how your programs behave. So now the real question, what are you building? You've been through a number of episodes by now. Let me know what you're building in the comments. Make sure you come back for more episodes. Do subscribe, and yeah, I'll see you in the next episode. Thank you for watching.